Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is power factor testing and advanced installation diagnosis. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. Oh, sorry, Charles, you still have your screen paused, so we're looking at the wrong
Oh,
slide.
oh,
No
oh,
worries. We got
handle.
everything set up for the run up to the webinar.
There
Forgot
we
to
go.
take a break off. So on the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, the certificate of attendance, copy of the presentation, and a link to the recording of this webinar will be sent via email to all attendees in 2 business days. Our presenter today is Charles Nybeck, Applications Engineer. Also to assist with the question and answer session, we will have joining us Dinesh Chajer, Technical Support Group Manager, and Volny Naranjo, Senior Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, Charles.
Thank you. So my name is Charles Nybeck, and I'm an applications engineer here at Megger. And as Michael said, today we will be discussing power factor testing and advanced installation diagnosis. Let's go ahead and get started with an outline. First, we'll start by talking about installation diagnostic methods, including time domain and frequency domain testing methods. Then we'll move into frequency domain transformer installation diagnostics, where we will discuss power factor fundamentals as well as power factor test methods. From there, we'll move into the advanced transformer installation diagnostics, where we will talk about narrowband dielectric frequency response, individual temperature correction, and voltage dependence factor. Then we'll go ahead and finish it off with covering the Delta 4000 power factor test set, where we'll discuss the hardware, test connections, and the software. Starting with the installation diagnostic methods, there are several different installation diagnostic methods, and on the left here we have our time domain methods that include installation resistance, polarization index, step voltage, dielectric discharge, polarization, depolarization current, and conductivity. And what these test methods all have in common are these are all DC test methods that are independent of frequency, as opposed to the tests on the right here that are performed in the frequency domain that include line frequency, power factor, and dissipation factor, as well as dielectric frequency response. And for the purposes of this presentation, we're going to take a look in the frequency domain. Before we jump into power factor itself, let's take a look at a transformer's life cycle, where on the x-axis we have transformers at the age, and on the y-axis we have the stress and withstand level. At the top, you'll see the black bar here that indicates the design withstand of the transformer, and in blue you have the actual withstand here. That shows a decay with the actual stresses shown in gray, as well as the incidences that cause these abrupt decays within the withstand. You can see that the normal end of the life of the transformer is here, but if one of these incidences were to occur towards the end of the life, you could see a premature failure in the transformer. Or in the case of your undetected gasket leakage incident here, if it could cause a defect that would cause further decay or an exponential decay of your withstand and could cause premature end of life. Now, testing and diagnostics could be introduced, and this could allow for field action and factory repair that actually fixes or increases your withstand and then extends your transformer life past your normal life. And this really highlights the benefits of testing and diagnostics for your transformer assets. Now let's go ahead and start moving into the power factor fundamentals. When we talk about power factor, what exactly is a power factor? Power factor is a form of the AC testing that measures leakage current or loss current of an insulation. And the intention of the power factor measurement is to determine the integrity of the insulation, where the ideal insulation would not allow any of this leakage current to flow. When we talk about the ideal insulation, we can look here where you have your primary side windings and your secondary side windings that are separated by a dielectric, which is the insulating materials in between. And essentially what this looks like is two potentials that are separated by a dielectric, and the classic case of this is a capacitor. And with a capacitor, if you apply an AC voltage source, you're going to get a 100% capacitive current here that leads the voltage, because the current must first flow through the two plates where the charge is stored right here, and only after that does that charge accumulate do you have your voltage difference. So the current, if you will, gets a head start on the voltage, and in the ideal situation leads your voltage by exactly 90 degrees. This is important because power factor is defined as the cosine of the phase angle between the voltage and the current, or the relation between the resistive current and total current. And for the ideal situation shown here in the right-hand corner, the phase angle is 90 degrees, and the cosine of 90 degrees is 0, showing that power factor is 0 for an ideal insulation. Another way to look at this is the relation between the resistive current and the total current. Well, here in this situation, or the ideal situation, the total current is the capacitive current, so there is no relation between your resistive and total current, and therefore, again, your power factor is 0 for an ideal insulation. Now, we know that in the practical situations that there is no such thing as an ideal insulation, meaning that a small amount of current is going to flow through the insulation known as the leakage current. And leakage current is comprised of two components, the resistive current and the capacitive current. And we know that the capacitive current is 90 degrees out of phase with the voltage. The resistive current is in phase with the voltage. And we also know that the capacitive current is due to the inherent nature of the capacitive nature of the insulation. So where does the resistive component mean? And that represents the losses of the insulation. That could be the presence of moisture, contaminants, partial discharge activity, or just inherently polar materials. Taking a closer look at the practical situation, you can see here, as stated before, that the resistive current is in phase with your voltage, and your capacitive current is out of phase with your voltage. On the right-hand side, you can see we have a theta angle and your delta angle. The cosine of your theta angle is your power factor, which again is also the resistive component over your total current. And you have your dissipation factor, which is in relation to your delta phase angle, which is the relation of your resistive current to the capacitive current. If we take a look at this situation, as we said earlier, we have our resistive current in phase with our voltage, our capacitive 90 degrees out, which is going to have a resulting total current in green here that's going to have a phase angle between, that's going to be less than 90 degrees, but greater than the phase angle, the in phase angle, which is going to result in a cosine of theta that's going to be greater than 0. And here, I would like to just take a moment to look at the situation for power factor where you have a power factor of 0.25%. Looking at this as the relation of the resistive current to the total current, you can see that the fraction to the right here is 1/400, which means that the resistive component of the total current is 1/400. So it just kind of shows exactly how much of the total current is the losses, or that loss current or leakage current, or your resistive component. When we talk about transformer insulation in particular, we know that it consists of both oil and cellulose. And an insulation system's permittivity is dependent on the transformer's geometry and individual permittivity. And taking a look at this diagram, you can see we have the low voltage windings here and the high voltage winding here, and separating it, you have your oil press board barriers and press board spacers. So this kind of highlights again the capacitive nature of the insulation, where you have two potentials separated by your dielectric. And the insulation can be modeled based on the knowledge of the geometry and the permittivity of the individual insulating materials. The model is known as the XY model and is used to represent the total dielectric response of an oil-impregnated paper insulation system. I won't get into great detail, but the XY model is shown to the right and is comprised of 4 capacitors in parallel and in series. And the real takeaway from this is that you can derive this equation using the model, which shows that the permittivity of the insulation system is a function of frequency and temperature. And this will come into play a little later in the presentation. Previously, you heard me mention power factor and dissipation factor. And you may be asking yourself, are these interchangeable? We saw the different formulas, so how close or what's the relation between them? And this really drives that home. Here you have a plot of power factor versus dissipation factor. And it looks like they line up pretty well until maybe the 60-degree angle mark. And at this point, if we take a closer look at the higher angle, or between 80 and 90 degrees, we can see now we have zoomed in between 81 and 90 degrees. And if we look at the lines, you have power factor in red and dissipation factor in blue, and they really don't start to show any deviation until above 10%. So essentially, power factor and dissipation factor are going to be about the same or the same until you start to get above 10%. Next, we'll look at an example of the power factor testing. When performing a power factor test, it's essential to short your high side windings and your low side windings respectively. But what we didn't see before in the previous case is the ground of the transformer chassis itself. So we've already known that between the windings themselves, we have a dielectric insulating material. But how about between the windings and the ground? If we look here, we can actually see that we have insulating material between the windings themselves, but also between the windings and grounds respectively. So you have your high to low, your high to ground, and your low to ground insulation that can be represented using the capacitors due to the capacitive nature. So if we put these together, we get this model here, which is the 3-terminal capacitor model that models the insulation between the nodes with a capacitor, like here, where you have your high-low, your high to ground, and your low to ground. And this is the same, just a different visual. So now that we've went through the power factor fundamentals, let's go ahead and take a look at the different power factor test methods. When we talk about power factor test methods, there are 3 different methods of testing: the ungrounded specimen test, or UST, the grounded specimen test, or the GST ground, or the grounded specimen test with guard connection, or the GST-G. Let's take a look at these individually. First up, we have the ungrounded specimen test, or the UST. In this situation, we have sine wave, or our applied voltage on the high side, and we can see the measurement lead in red and the ground shown in green. So taking a look at this, we can see the total injected current here is going to split because of the 2 paths between high and low and high and ground. So now we have 2 current components. As they flow through, we can see that the leakage current from the high to low is the only current component being measured, while the leakage current from high to ground is being bypassed through the ground lead and bypassing the ammeter. So in the ungrounded specimen test, or the UST test, the measured current is going to be the high to low leakage current. Now in regards to the grounded specimen test, or the GST ground, we have a similar situation, but we can see that the measurement lead and the ground lead actually come together before the ammeter. So this time, when we have our total current being injected, we have our 2 current paths between high and low and high and ground. And this time, our leakage current from high-low and high-to-ground come together to go through the ammeter. So in this situation, our measured current is going to be the leakage current from the high to low plus the high to ground. Lastly, we have the grounded specimen test with guard connection, or the GST-G. In this situation, we can see the measurement lead in red actually being guarded and bypassing the ammeter, where the ground lead actually has the path of the ammeter. So in this situation, if we were to have our total current being injected, we have our 2 current paths, again, our high to low and high to ground. This time, our high to low leakage current will bypass the ammeter, and therefore only the leakage current from high to ground will be measured. Therefore, our measured current is our leakage from high to ground. Now this test method is used to separate the total values from the GST method, the previous method we just looked at, for better analysis. And what that means is the GSTG is equal to the grounded specimen test and the minus the ungrounded specimen test. And we're going to take a look at that in the summary here. So here on the left-hand side, you have your ungrounded specimen test. So we have our applied voltage on our high side, and we can see that the ammeter is from our high to low. So here we have the measurement on our high to low insulation. If we look at the GST ground, we see that the applied voltage is still on the high side, but this time both our ground and our measurement leads go through our ammeter, and that means that we are measuring both the high to low insulation as well as the high to ground insulation with this method. Lastly, again, with the GSTG, or the grounded specimen test with guard, we've guarded our red measurement lead, and we're now measuring through the ground lead. That leaves just the high to ground. So if we look, again, our GST ground minus the UST, or ungrounded specimen test, leaves the grounded specimen test with guard. So this kind of is a self-check when testing, just to be sure that the connections were right and the test was performed right, because those values should come out very similar, if not the same. So now that we've looked at the different test methods for power factor, let's take a look at the actual data gained from a power factor test. A power factor test provides more data than just the power factor value itself, such as capacitance. Capacitance is a measurement that gives insight into any physical changes that have taken place between the tests. Also, capacitance can indicate a change in the permittivity of the insulating materials. We'll take a look at this a little further into the next slide. Also, power factor measurements can give you information on the leakage current, which is the gradual transfer of the electrical energy across the boundary, normally viewed as insulating. The resistive component of this leakage current is going to increase with age. And again, we'll take a look at that on the next slide. Finally, the third piece of information that is provided, aside from the power factor value itself, is the total watt loss, which is the total amount of power dissipated as losses. So now that we know about this data, what actually causes a change in power factor or capacitance? So when we talk about power factor, there are several factors that can lead to an increase in power factor, but overall, power factor increases due to an increase of the resistive current to the total current value. So looking again at our example here, we have our capacitive current we know is 90 degrees out of phase. We have our resistive current, which is in phase, resulting in our total current. Now, what happens when the insulation ages and the resistive component of that increases? Well, it looks a little something like this, where our capacitive component of the current has stayed the same and the resistive component has increased, resulting in a higher power factor. And you can see that by the change in the angle as well. Not only has the resistive component increased, which we know power factor to be the resistive component over the total component, but also look at the decrease in the phase angle of theta. So we know that cosine of theta is also power factor. So in here we can see that we have an increase in power factor based on the increase of the resistive current to the total value. Next, we'll look at the capacitance. With capacitance, it's a function over here of the permittivity of air as well as the relative permittivity of the material, the dielectric material, the area of the electrodes, and the distance between them. So if the permittivity of the oil were to decrease with age, then you could see a decrease within your capacitance. Also, if the distance between electrodes were to change, the overall capacitance would change. For instance, looking at the capacitor down bottom, we can see the plates are X far away from each other. If something were to happen physically to cause these plates to change distance, now the distance has increased. We can see distance in the denominator of the capacitance formula. This distance has increased, therefore the capacitance, the total capacitance, will decrease. So capacitance can give you insight into the condition of the permittivity of the oil, which is the condition of the oil, as well as any physical changes that may have happened within your transformer. Now we've been talking about transformers, but I'd like to just take a slide to just talk about the different applications for power factor, because it's not solely just for transformers. It can be used for power and distribution transformers, but also can be used for instrument transformers, rotating machines, bushings, cables, capacitors, circuit breakers, surge arresters, porcelain insulators, and oil itself. So power factor has many applications, but for this presentation, we're going to focus on transformers. That being said, let's take a look at a couple of the standards. On the left-hand side, we have the IEEE Guide for Acceptance and Maintenance of Insulating Mineral Oil in Electrical Equipment, that discusses power factor testing. And also, to the right, on the right-hand side, we have the IEEE Standard Test Code for dry-type distribution transformers and power transformers. Now, in the middle, we have the more popular, the IEEE C57-152, or Guide for Diagnostic Field Testing for Fluid-Filled Power Transformers, Regulators, and Reactors. Let's take a little bit of a deeper look into this guy. Looking into the IEEE Standard C57-152, we can see the Table 18 contains the nominal and serviceability service age limit for power transformer insulating power factor. Looking at the insulating liquid of mineral oil, if your transformer has a kV rating less than 230 kV, your nominal to new power factor limit is going to be 0.5%, while the serviceability age limit is 1. If the transformer utilizes mineral oil and is rated above 230 kV, you can see the nominal or new power factor limit being 0.4%, while the serviceability age limit is 1%. And then taking a look at the natural ester oils, you have for all of your kV ratings, likely due to the natural ester oils being able to contain more moisture, the nominal and new power factor limit is 1, as well as the serviceability age limit. Also, I'd like to take a look at the note down here where all power factors are corrected to the 20 degrees C, except for the natural esters. Taking a look further into the temperature correction tables were removed from the C57-152 standard in 2010 with a statement printed in the 2015 version, and you can see that below. I just want to take a look at the first and last sentence, where the first sentence states that experience has shown that the variation in power factor with temperature is substantial and erratic, so that no single correction curve will fit all cases. So that takes that out right there. In the last sentence, we have temperature correction for power factor results for trending basis may be applied by the purchaser. So the standard recommends performing the test at 20 degrees C, but as we know, depending on the location, this may not be possible. As you go further north, it's likely to be more cold, and if you're in Texas, like we are, or I am, then it's likely to be more hot. On the other hand, though, there is the individual temperature correction that can be used to correct readings to 20 degrees C. That is a unique function utilized by Megger instruments. This really allows for the ability to trend the results, because you can normalize all your results or correct them to the 20 degrees C value, and that really helps with trending, as you don't have to have varying power factor based on the weather or the season that you're performing the test. And we'll take a look into the individual temperature correction a little bit later as well. So now I'd like to take a moment, now that we've discussed power factor, and talk about some of the power factor limitations. Now, power factor has no direct correlation to moisture and is not acutely sensitive to problems at line frequency. Also, there are no guidelines on what the next step is when you get a questionable reading. So we saw that this IEEE C57-152 serviceability standard was 0.5 for, or nominal and new, sorry, is 0.5 for transformers of less than 230 kV. So what happens if you get a power factor of 0.5 or maybe even 0.6? Do you get rid of the transformer at that point? There's no real defined next step. Also, when a problem is indicated, it's nearly impossible to characterize, leaving you with the question of what happened to make my power factor change. And this kind of leaves that question unanswered. Lastly, or ultimately, power factor also has a limitation in the fact that it's an averaging test. So let's look at these students over here. We got 5 students that had tests and got their grades back, and 4 of those 5 students passed with 100s. The one, though, here in yellow, had a 50 on his exam, so he did not pass. But if you stop and you take the average of all 5 of these students, their exam grade is 90, which is an A and is passing. If we look at that in terms of insulation, then you have a localized problem, which is this guy here in yellow, but the rest of the insulation is perfectly fine, then your power factor may come up just fine and may not really, and kind of mask the ability to see the isolated issue. And this really impacts the ability to discriminate between localized defects as well as widespread general aging and deterioration. So now that we've talked about power factor fundamentals and test methods, let's take a look at some of the advanced transformer insulation diagnostics, starting with narrowband dielectric frequency response. Here, and the narrowband dielectric frequency response is an evolution of power factor extending it both ways around the 60 hertz or line frequency value. And the range is from 1 to 505 hertz. And what this offers is higher sensitivity to the insulation problems, as well as earlier detection during the deterioration stages. And also that question of, is my power factor really good or not, becomes a little more clear with the higher sensitivity and the power factor across the range. And 10 measurements in the range of 1 to 505 hertz, it takes approximately 3 minutes. Let's take a look. On the right-hand side here, we have a plot that has the 60 hertz value in the black dotted line, and the gray dashed line is the 0.5 accepted limit. Here we have our 60 hertz power factor value just above 0.2. Now, let's take a look at the 10 measurements that were taken for our narrow band dielectric frequency response between 1 and 505 hertz. Now we can see quite a bit of a difference. If you take a look, our 60 hertz value is 0.2, but our 1 hertz value, you can see significantly more sensitivity and is at 3. So this gives you a little bit more insight into the full condition of the insulation by not only having your 60 hertz value, but also having the higher sensitivity of the 1 hertz that allows you to determine whether or not there's need for action based on the power factor or your narrowband dielectric frequency response measurement. Here we have narrowband DFR and how it looks like as a transformer ages. In this condition, we had a transformer that was overloaded for 6 months and monthly measurements were taken. 500 hertz is here, so the cutoff is here, but we can obviously see that our 60 hertz value does not change very much throughout the 6 months. But if we look at the 1 hertz value, it goes from 0.469 or 0.47, let's call it, to 6 months later being at 3.61, while your 60 hertz value doesn't change very much. Also, you can see the trough or the low part of the curve migrate towards higher frequencies as the aging takes place. So again, highlighting the advantages of narrowband DFR and the higher sensitivity at the low frequencies, as well as the better picture or broader picture of rather not just looking at the 1 point here at line frequency. Next, let's take a deeper look at the individual temperature correction or ITC. As we've already stated, the industry used to use conventional correction tables, and those were removed in 2010. Now, what can be used instead is individual temperature correction, as we mentioned before, utilized by the Megger instruments. Individual temperature correction, or ITC, allows for accurate temperature correction between the ambient temperature range of 5 degrees C and 50 degrees C. And the way it works is based on the Arrhenius equation here, but we can look at it graphically here. Basically, the shape of the dielectric response does not change very drastically with temperature, but you can see a shift in the frequency. So if we take a look, we have our 20 degrees C, 40 degrees C, 60, and 80 degrees C. As the temperature increases, we can see a shift towards higher frequencies. So if we utilize the narrowband dielectric frequency response that we just took before or showed on the previous slide, and we already have the sweep frequency, or the frequency sweep, then we can translate that to a change in or a shift in temperature, allowing to accurately correct temperature to 20 degrees measurement, anywhere between the ambient temperature of 5 to 50 degrees C. Here, we're looking at the ITC, or individual temperature correction curves for typical transformers. We can see that the typical correction tables for transformers is shown here in purple. Now we have 4 other transformers ranging from manufactured dates of 1977 all the way to 2005 with various MVA ratings. And you can really see that none of them really align very well with the correction tables that were previously published. What that leaves you with is, on the newer transformers, you're going to end up overcompensating, and on the older transformer, you're going to end up undercompensating. But you can really see why the need for an individual temperature correction that is specific to the asset that you're testing is the benefit of the ITC. Rather than having a temperature correction for all transformers based on some of their nameplate information, the narrowband dielectric frequency response allows for you to choose an ITC, or an individual temperature correction factor, for that specific asset, which really highlights the benefit of the individual temperature correction. Next, let's take a look at the voltage dependence factor, which is essentially a power quality of the leakage current measurement. On the right here, we have an example of the measurement of a leakage current, and you can see these kind of blips or distortions within your measurement. Now, what happens is this equation is utilized, which compares the fundamental frequency of the leakage current to its harmonics. And if this value is high enough, then it suggests to run a automatic tip-up test, in which an automatic tip-up test is just a dissipation or power factor measurements at various voltages. For instance, if you were to end at 10 kV, you could do steps of 2, 4, 6, 8, and 10 kV to see how your power factor responds to the voltage. And this is a diagnostic test method that is typically for nonlinear or high loss insulation, and allows for the differentiation between moisture and partial discharge related issues. So now let's go ahead and take a step and look at the Delta 4000 power factor test set itself. Here we have the Delta 4000 power factor test set with the control unit on the left and the high voltage unit on the right. Let's go through its individual ports. Here we have the mains, that powers the control unit, followed by the COM ports, one being Ethernet and the other being USB-B. Here we have the PC control, where you can choose to control the unit via an external PC or an internal PC if the option is available. Next, we have our test ground that connects to the control unit and is connected to the test object's ground. It is important to highlight that for safety measures, it is necessary to perform a test. It is necessary that all grounds must be common. That means that the test ground be the same as the ground between the control unit and the high voltage unit, so that you don't have any open ground. And that is determined by this light here. This LED is the open ground LED, in which, if there were an open ground, is illuminated, and once the grounds are all common, will turn off and allow you to perform a test, given that the interlocks are pressed. And we'll look into those a little later. Here we have the ground that interconnects the control unit and the high voltage unit. Now we have the high voltage power that provides power to the high voltage unit, followed by the high voltage control, which controls the high voltage unit. Next, we have the red input lead or measurement lead. This corresponds to the red measurement lead when looking at the power factor test methods. This is that measurement lead or red lead that was shown graphically in those test methods. Then we have the interlocks that I had mentioned previously. Again, for safety measures, it is required that both these interlocks be depressed before a test can be executed. So there are three conditions to performing a power factor test for safety reasons. One is all grounds must be common, and two is both of these interlocks must be depressed. Once all three of those conditions are met, the test can be performed. And we'll look at that a little bit later as well. Then finally, you have the breaker for the mains on the control unit. Next, let's take a step and look at the Delta 4000, where the control unit is on top and the high voltage unit is on bottom. Here we have the high voltage cable, which is simply inserted and slid into the high voltage unit and locked into place via a locking mechanism. It's just a pull and release. The high voltage cable has many different terminations depending on your application that can range from a hook, variable Kelvin clamp, as well as small clamps for bushing adapters. Next, let's take a step and look at the power factor test connections. Here we have an example of the power factor test set, the Delta 4000 on the left, with the control unit on top. As I said, with safety, we have our test ground that is connected to the chassis or the ground of the transformer, seen in green. Next, you have your measurement lead in red that is applied to the secondary bushings. Now, it is important to note that when performing a power factor test, the primary side bushings must be shorted and the secondary must be shorted as well. So here we have our secondary bushings shorted and our measurement lead showed in red attached to that. Then we have our high voltage unit underneath, and the high voltage cable shown in black that's applied to the primary side bushings that are also shorted together. Now, in this test configuration, we know that we're going to apply voltage to the high side, and depending on the test mode, are either going to measure the high to low or the high to ground, or both, depending on which mode is utilized. Here we have the test connections again, same connections, just a different diagram to walk through. Again, first we have our ground connection for safety. So we have our interconnected grounds between the unit, and then we have the ground attached to the chassis. Next, we have our measurement lead shown in red attached to the secondary side of the bushings. Notice that they are all shorted. And then finally, we have our high voltage that is applied to the primary side, and notice that all the primary bushings are shorted. So again, in this situation, we are applying high voltage to the primary side, measuring on the secondary, and have our ground as well. So depending on the test mode, we could measure the high to low, a high to ground, or both as well. Now, let's look into the power factor or the Delta 4000 software. The Delta 4000 utilizes PowerDB as its software. You can see here, and when opening the software, that you have the input of your nameplate data, which is necessary, for instance, your vector diagram to determine what vector diagram or configuration your transformer is in. You have your voltage rating, your power rating, your current, a chance to set up your taps, how many you have, what's nominal, of course, if you have a de-energized tap changer or on-load tap changer, and then the rest of your nameplate information. And one thing I'd like to highlight here is the oil temperature. It's very important if you want to accurately perform temperature correction to input the proper oil temperature. If we scroll down further, we'll come to the overall test setup seen here. By default, you'll notice that the temperature correction tables are being utilized and the narrowband dielectric frequency response is turned off. All we have to do to change this is simply click those boxes, and the test form will look more like this, where we have utilized the individual temperature correction as well as the narrowband dielectric frequency response functionality. And you can notice that we have all of our tests, your high side tests here, where you have your grounded specimen test ground, where you measure your high insulation from your high to ground and your high to low, your grounded specimen test guard, where you're measuring your high to ground, and then your ungrounded specimen test, measuring your high to low insulation. And you have your low side tests, very similar to the high side tests. Now, if we want to perform a test, for instance, the high to low insulation test, you would click the test number 3 here, and a window similar to this would pop up, which is your measurement overview. Notice the test mode is still the UST. You can see down bottom that we have options to start. We can look at the hookup diagram, and then notice that on our frequency, we have multiple frequencies selected or to be tested. just showing that we are utilizing the narrow band dielectric frequency response. If we were to click start, a window would pop up with the interlock to start measurement pop up. As we mentioned previously, there are 3 conditions that must be met to perform a power factor test. Both interlocks must be depressed and the ground loop must be closed. For the purpose of this, I went forward in simulation mode. So we're back to our measurement overview. Notice the top left-hand corner, it still says delta 4000. Well, now the test measurement will start and you can see measurement in progress. When the measurement is in progress or our power factor measurement is being performed, even with the narrowband dielectric frequency response selected, the first measurement will be your 60 Hertz measurement, as seen here. So still your UST mode, now your 60 Hertz value, and you get your power factor, your current, your leakage current, your capacitance, and your watt loss. Then it'll move to the 10 measurements that are between or from the range of 1 to 505 Hertz, seen here. So again, we have our power factor, our leakage current, capacitance, and the watt loss for the power factor measurement of these frequencies. Once the test is performed on all possible tests, the overall test set or table will fill out and look something similar to this, where you have your capacitance measurement, and you can see that here you have your combined capacitance measurement, which is comprised of both of these. And then you have your power factor that's measured, and then your 20 Hertz corrected value. Since I was in simulation mode, my correction factor was 1, but this would be your individual temperature correction that is specific to the asset that you are testing. Then to the right, we have our direct measurements that include our milliamp measurement for our current, and then our watt loss measurement. Then finally, to the right of that, we have our percent VDF, which is our voltage dependence factor. Again, since I was in simulation, it came out as 1 for my measurements, and you can see that they turned red, indicating that it is being suggested that an automatic tip-up test be ran. If we scroll down from there, we can see a window like this that shows the actual narrowband dielectric frequency responses being highlighted and shown graphically. And you can see again from 500 to our 1 Hertz, we have our 60 Hertz value here. And then as the sensitivity towards the lower frequencies increases, we have our higher power factor at our 1 Hertz measurement. So finally moving on to the Delta 4000 summary and highlights. The Delta 4000 is a lightweight, rugged 2-piece design where you have your control unit on the top there and the high voltage unit on the bottom, where the control unit is slightly lighter due to the high voltage unit containing a transformer. Both coming together though at just under 80 pounds. It was designed and manufactured with standards such as safety standards, the EMC standards, and shock and vibration standards in place. The Delta 4000 is a power factor test set that's capable of 12 kV and 300 milliamps and measures capacitance or inductance, current, and watt loss. Is capable of narrowband dielectric frequency response from the range of 1 to 505 Hertz, individual temperature correction in the ambient temperature range of 5 to 50 degrees C, and utilizes the voltage dependence factor functionality. Next, we have the input power of the Delta, which ranges from 90 to 264 volts, from 45 to 66 Hertz, and no more than 16 amps. It is important to note that there is no loss in the performance when the Delta 4000 is utilized with the portable generator, because the Delta 4000 takes the AC signal, rectifies it to a DC signal, and inverts it back to its own clean AC signal to be utilized and run off of. Alrighty. Here we have our contact information. Any questions?
All right, thanks a lot. So at this point, our presentation portion of our webinar is officially concluded. We'll now take some time to answer as many of your questions as possible. If you do have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or a quote on any Megger products. A copy of this presentation, certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars on our website at us.megger.com/webinars and register for our next webinar in this series on load tap changer condition assessment. The presenter will be Ollie Bensler, and it will be occurring this Friday at 10 a.m. Central Daylight Time. All right, so let's jump into your questions. The first one I have is going to be for Dinesh. Dinesh, are the Megger and other industries available PF temperature correction factors the same? Dinesh, doesn't look like we can hear you at this time. All right, it looks like Dinesh is having some audio issues. We're going to jump over to the second question
Michael,
for a second. Yes.
Michael, I can take that question.
Oh, cool. Thanks, Holden.
What was the question, please?
The question was, are the Megger and other industry available PF temperature correction factors the same?
Yes, so initially there were some, or there are still some tables available that were developed from databases of transformer results from years and years of data recollection, and that's the values that were used initially, and those are the values that were considered in the standard, and those are the ones that Charles mentioned, that the standard, after revision of the document, decided to mention that no tables or no unique values were applicable to all transformers, and they decided to remove the tables from the standard. And they recommend testing around the reference temperature. Of course, this is not possible or not practical all times, and that's when Megger decided to come up or look into another alternative, and that's when we developed the individual temperature correction method, which we explain in this presentation. So if we are talking about the tables, yes, they are the same, and they are still used, as Charles mentioned in one of the slides. The tables, we still have them there, but you have the alternative to use the individual temperature correction if you want a better accuracy or a better correction there.
Thank you, Volney. While I have you, the next question is also going to be for you. Will tan delta values at other frequencies be comparable to limits? If tan delta values are already bad, do we need narrowband DFR?
Okay, so the first part, the first question, no, they are not comparable. Power factor is also, as it was shown with the permittivity equation, power factor is dependent on frequency and temperature. And well, traditionally we have been doing the test always at the same frequency, so we were not used to see the dependence on frequency. We were just seeing the dependence on the temperature side, because depending on when we are testing, we will always have a different temperature on the transformer. So they are not the same at different frequencies, and that is very important to consider when reviewing the results. And one other thing that has to be considered is that the values, when you perform narrowband DFR, you always have to consider if these values have been corrected for temperature. So those graphs that Charles showed, those were also corrected by temperature. And if the delta value, the tan delta values are already bad, do we need to do a DFR? Well, that depends on what it's being considered as bad. If they're just a little bit above the limit, that we are established, or the standard has established, that the 0.5% or something like that, then that's where the power factor has the limitation that you don't know if it's really bad, or if you have a very small increase, or the changes are starting to the values are starting to change, but they're very small, then you have the uncertainty of what to do. So that's when it's preferred to do, or when we recommend to perform narrowband DFR, to be able to get more information and to make use of that higher sensitivity that narrowband DFR offers at the lower frequencies. So to summarize, there's the values at different frequencies are not comparable to the 60 hertz limit, because they are not the same, they are not comparable. And then if you have a power factor that it's not clear, or that you have some uncertainty, it is better to run a narrowband DFR to get more information.
Thank you, Volney. Dinesh, our next question's for you. What about power factor of natural esters? Are separate standards available for natural ester in IEEE?
Good morning, everyone. That's a very interesting question. The reason why I say that is that nowadays you see more and more transformers being utilized, or having natural ester as the insulation medium instead of mineral oil. So this question is very valid. One thing I would like to mention is that when you talk about natural ester, FR3 or any other oil, they are more polar in nature, and because of those reasons, your power factor values are going to be higher for any transformer that has natural ester oil in it. And the slide number 30 that Charles showed, IEEE C57.152, it does talk about the limits for the different voltage class, and if you have natural ester oil in that, what would be the values. I believe it was like 1% value, and there has been a lot of research done on this thing, and it has to do with a number of different variables. One is that whether you're talking about distribution class transformer or power transformers, because the ratio of oil to paper is going to be different for those transformers, and that can impact your power factor values, as a power transformer would have considerably large amount of oil as compared to distribution class. And if you look at the ASTM standard, and if you were to just test the mineral oil versus the natural ester, the values of those tests at 25 degrees C and 100 degrees C are also considerably higher for natural ester. Just to give you an idea, that at 25 degrees C for a new fluid, mineral oil has an acceptance value of 0.05% as per the ASTM standard, and for natural ester is 0.20. And likewise, if you talk about in-service or new equipment oil, the values are considerably higher for natural ester. As a rule of thumb, it's not anywhere in the standard per se, but for natural ester oil-filled transformers, you should use a rule of thumb of having twice the value of the transformers that have mineral oil in it. That's a approximate rule that you can use for natural esters.
All right, thank you, Dinesh. Charles, our next question is for you. Can the ground cable be placed on any station ground when performing PF measurements?
So the ground cable must be placed on the test specimen ground, and all the grounds must be common. So it is important to remember that the ground for the control unit must be the same as the ground of the high voltage unit, and then attached, on the ground or the chassis of the transformer as well, or the test specimen. Otherwise, that light that we saw, the LED that indicates the open ground, will be illuminated, and only once you have a common ground will that light then turn off and allow you to perform the tests. So you can't place it on any ground. It must be the ground of the test specimen, and then you have to make sure that all of the grounds that you have for your test and your test specimen are common, so that way you can safely perform the test.
Thank you, Charles. Volney, do PF tests need to be performed on a yearly basis?
Well, this is one of those questions that the answer is it depends. Depends what is the condition of the insulation. If it's an insulation that is deteriorating fast, or if it's under certain conditions, or if it is operating under certain conditions that might be deteriorating the insulation faster, then you need to put this transformer on a special testing regime that you want to look more into, get more results. Usually, I've seen utilities that they do testing every 2 years. Other utilities do testing every 5 years. It also depends on what are the testing practices. Any data that you collect on insulation power factor, it will be beneficial for the future. You can trend values, you can collect data and see if there's any deterioration. So you don't have to do it every year, and it will depend on what is the condition of the insulation and what actions you want to take and what is your plan on the transformer. But collecting data and running tests on a transformer is beneficial. So I don't want to say that you don't have to do it, but it's beneficial at certain point.
All right, thank you. Dinesh, can I perform a PF test on medium and low voltage transformers?
So a simple answer to that is yes, you can perform a power factor test on any insulation that you wish. You can take a piece of wire and apply a voltage on that. Obviously, don't want to exceed the rated voltage of that specimen. So the simple answer is yes, but there is a lot more detail involved behind that. If you look at the IEEE C57-1200 standard, it says that power factor should not be considered for distribution class transformers. So depending upon what standard you are looking at and how much historical data you have, that would define whether you should perform the test for insulation assessment or not. I will give you an example that if I have a dry type transformer and I have a number of those dry type transformers available from the same manufacturer, then it makes sense to do a power factor measurement, because then I can do some comparative study and come up with some benchmark values. We also need to consider that when you talk about dry type transformers, the values can vary drastically. You can have as high as like 8% power factor values, and some of those transformers would still work just fine. So setting up the limit becomes a challenge. You can certainly run the test, but defining the limits or the analysis criteria is a challenge. And that's why I said, like, if you have a whole fleet of dry type transformer with the similar ratings, then it makes sense to do that. The other thing that you can do is that you can perform a tip-up test on dry type transformers. That would help as well. So to kind of summarize this question, yes, you can perform the test on medium and low voltage transformers, but you have to be careful about how you analyze the measurements.
Thank you, Dinesh. Charles, why do we need temperature correction factor?
So temperature correction factors are necessary because, as we saw, the permittivity of the insulating materials themselves is frequency and temperature dependent. So also we just by the IEEE C57 152 statement that we know that it's temperature dependent, and the standard itself also says that the test should be performed at 20 degrees C. And since it's likely or difficult to perform the test at 20 degrees C, the idea is to correct that, or that temperature or that value, to a 20 degrees C power factor value. That way you can have a nominal value for power factor and be able to compare these power factors down the way. If you were to perform a power factor test without any temperature correction, then your power factor could change based on the season, based on the ambient temperature outside, or based on the temperature, the loading of the transformer, depending on how hot it may have been, how hot it, or how much it set before it was tested. So all these come into play, and it's impossible to get a transformer in the same condition to test every time. So rather than to have the transformer in the exact same condition every time to test, you translate your values, or the measurement that you received, into a 20 hertz or 20 degrees C value. That way it improves your ability to trend those results and compare those results down the line.
All right, thank you, Charles. Dinesh, is there any alternate way to perform power factor testing?
To answer that question, I would go back one step, and the purpose of power factor testing is to identify the condition of the insulation, and you can check the condition of insulation with different kind of test methods. There are DC insulation testing available. High pot test is another one. And I'm not talking in general, not talking specifically only on transformer. In general, there are a lot of other methods available to check the condition of insulation. PD is another method that you can use. But when it comes to power factor testing, and the reason why it is so popular is its ability to trend and analyze the measurement. There are alternate ways to perform power factor testing, in the sense that you can vary the voltage and see how the insulation reacts to the change in voltage, which we typically call as the tip-up test. Charles also talked about frequency-based power factor testing, where you vary the frequency and perform the power factor testing to analyze the results in a better way. And even in that, there is a narrow band dielectric frequency response, which is a limited frequency range from 1 to 500 hertz. And then if you expand that frequency range, you also have the ability to measure or to estimate the moisture present in the cellulose. So there are different variations of power factor testing. And if you are trying to talk in general about insulation assessment, there are other tests available like DC insulation, PD, high pot. On cables, you do VLF testing. So there are just a number of other tests available that can be used for insulation assessment.
All right, thank you, Dinesh. Charles, what is the maximum voltage of frequency sweep?
So the voltage of the frequency sweep is actually depends on the how low in frequency that you're going to go. So you can go upwards or above 250 volts. As we saw, it was just the default there. But the voltage, the max test voltage is 12 kV. But it is dependent upon frequency. The lower in frequency you go, the more limited you're going to be in the max voltage that you have. So it's dependent upon the frequency and how low in frequency that you're going to perform the test.
All right, thank you. Volney, can you show a power factor value corrected by table and one ITC to be able to better visualize the differences?
Well, in the presentation, there was a slide that showed in the section of temperature correction and we were talking when Charles was talking about the individual temperature correction that showed the correction factor curve from the tables, and then the different correction factors for different transformers, or the curves for the correction factor of different transformers under different aging conditions. So that will be a good example. The presentation will be sent to the attendees. And yeah, we have numerous cases or numerous examples that we can show if needed. We can individually, the person that asked the question, we can if we are contacted, or we can send him a couple of other examples to show the different results that are obtained with when testing a transformer, or when correcting a result with the tables and the individual temperature correction. One thing to highlight here is that the older the transformer and the more deteriorated the transformer, because the operation conditions, more difference is going to be compared to the tables. So in new transformers, really we have seen that there's not too much to compensate, and that's one of the reasons the standard, or that the IEEE removed those tables, that with new transformers there was some overcompensation applied. And but in summary, yes, we can provide more results individually to this person who asked the question.
Okay, thank you. And just as a reminder to all the attendees still here, we will be sending out a copy of this presentation in about 2 business days. So keep an eye out for that email soon. So Dinesh, our next question is going to be for you. What is the probable reasons for getting negative tan delta value?
I would certainly answer that question. One quick comment I want to add to the previous question is that farther away you are from 20 degrees C, more influence you would see, or more difference you would see between a temperature corrected value using tables versus the ITC method that Charles covered. So as you are, let's say you test at 35 degrees C or 40 degrees C, and you try to compensate for temperature using ITC and versus temperature correction tables, you can visually see the difference between the two. So the ITC is much more impactful when you're testing at higher temperatures, 35 degrees C, 40 degrees C. You would see a huge difference in the correction factors. Coming back to the question, what is the probable reason for getting negative tan delta value? If you go back and look at the theory of power factor testing, the best power factor that you can hope for is 0. So anytime you get negative power factor value, it's an indication that something is not right. And you get negative power factor values specifically, or many times you get negative power factor values on bushings. And the reason for that is that anytime you have surface tracking going on, or surface contamination or condensation on the surface of the bushing, it results in the surface leakage current. And if you remember, the formula for power factor is a cosine of phase angle between voltage and current. And because of the surface leakage current, what happens is that the angle between voltage and current exceeds 90 degrees. And if you take a calculator and try to calculate a power factor or a cosine of 90.1 degrees, you will see a negative value. So those are the reasons why you get negative power factor values. And one important thing I want to mention here is that it's not just about negative power factor value. Let's say last time when you did the testing, assuming the temperature is same, if your power factor value was 0.5%, and next year you go and the power factor comes out to be 0.35, I wouldn't be happy about that. Insulation cannot improve by itself. So if your value decreases, it also means that you have a problem, because again, it hasn't gone to complete negative, but power factor improving by itself is also a concern. So make sure that your values are either staying the same, or it should not be decreasing, because that's an indication of surface contamination.
Thanks, Dinesh. So Volney, our next question will be for you. What is the main purpose of the sweep frequency testing, and also for the tip-up voltage testing?
Okay, so the power factor testing has been a very useful tool throughout the years to diagnose the insulation of the transformers and many other insulations, but especially in transformers, that's been the main tool to evaluate or to diagnose the condition of the insulation. However, as we saw during the presentation, the power factor testing has some limitations, and most of the outcomes of when you have a power factor result that is increased, or that we detect a trending issue, or the values are increasing in the trend, then the outcome is always investigate. So we have to always further investigate. And at certain point, determining that investigate is difficult, because the limitations on power factor that we may not have a very good sensitivity, and then the correction factor issues. Sometimes we're not correcting correctly, and all of these things. Then we need more tools for investigation. In power factor test sets now can have that additional investigation tool. So without moving into other testing, without moving into or to have the ability to have a way to investigate the insulation right there on the spot while you are testing, without waiting for a couple of days for oil results, you can get more information from the transformer with the same test instrument. So that's what narrowband DFR gives you. It gives you the ability to get more information and see a wider spectrum of the condition of the insulation with one simple test that takes a very short time to perform. And tip-up testing is also another way to get more information. So when you run a power factor, you are if you are not looking into that power quality, into that quality of the signal that it's coming back to the transformer, you are losing some information. The instrument is doing that automatically for you. It's detecting if it is if there's any possibility of small partial discharges inside the transformer, and it's indicating that you may be able or to find out more with running a tip-up test. And tip-up test is going to provide you that additional information. So basically, narrowband DFR and tip-up test are advanced power factor testing methods that can give you more information and can give you the ability to investigate further that insulation on the spot.
All right, thank you, Volney. Dinesh, why do we test for a variety of frequency? Is there any reason to test for 1 Hertz to 470 Hertz?
I guess they say that they leave best questions for last. This is a very good question to ask. Why there is a reason for testing at various frequencies when my transformer is only going to see 60 Hertz? So the reason for us testing at different frequency is not that we are interested in finding the value at 25 Hertz or 70 Hertz or something like that. The idea is to see how the curve between power factor and frequency is behaving, and see the trend it is taking in the lower frequency. And I really, really want to emphasize on this thing that the most critical frequencies that you need to look at is in the range from 1 to 20 hertz. That's where the curve really starts to take off on problematic transformer. If you stop your testing at 20 hertz, you are not doing justice to the narrowband DFR testing. It's absolutely a requirement to run the test to 1 hertz, so that way you can get the full trace and see how the values are coming about. And as I said, like if your losses are increasing at lower frequency, it's an early indication that your power factor value at 60 hertz are going to increase later in future. So the whole idea of preventive maintenance is to pick up the problems at an early stage and prevent some of these failures. And that's what narrowband DFR does for the field engineers. It gives an early warning about what is about to come or about to show up in 60 hertz testing. So when you perform the power factor at various different frequency, you're getting an early indication by looking at the losses taking place in the lower frequency. And if your curve is shooting up high in the lower frequency, that's a problem, or that's an indication of some issue, and you need to be proactive in addressing that. And that's the reason why you should perform narrowband DFR testing every time you go out to perform your 10 kV 60 hertz power factor measurement.
All right, thank you, Dinesh. It does look like that's all the time we have for questioning. We apologize if we did not get to your question today, but we will be following up with you offline in the following week. But thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all for attending today, and have a great week.